So this morning we all heard fascinating talks, mainly concentrated around instrumentation, and this afternoon we are going to see the side of the applications. It's a great pleasure for me to introduce the first talk given by Stéphanie Durand about 30 years of global tomography, and it seems to be the mantle strengths. So let's listen to Stéphanie.
Thank you. Good afternoon, everybody, and thank you to the organizer for the invitation. I would like to start mentioning that I realized this morning that I actually was not born when Geoscope was deployed, so I'm not the best to talk about the evolution since Geoscope, and I was also still a naive child when the first global tomographic model was produced. So I gave this title 30 years of global tomography, but I have to acknowledge that I was more sensitive to the last 20 years. So there will be a little of bias in my presentation. And secondly, I also realized when I gave this title that it was not obvious what I meant by mantle drapes. And so I wanted to start by explaining the analogy I meant to do. So the drapes is, you know, when you put a fabric on an object, you will have these typical folds, and it's a very good exercise for drawers to try to reveal the complexity of the drapes. And you need to reveal the various amplitudes, scales, and the texture of the fabric. And when it is very well achieved, you can even guess what is the structure that is hidden by the drapes. And I thought that our work as tomographer is a bit the same. So we know that the mantle is very complex from, for instance, thermochemical convection simulation. And so you have various scales, various kind of heterogeneity, thermals, chemical, and we want to reveal this complexity using tomography and seismic waves. And so the image on the right is actually not a result of photography. I just played around with PowerPoint tools, but I found it could highlight the problems we face when we do tomography. Like sometimes we lose the continuity of the structure, or we have some artifacts, and so that's all the challenges. I mean, part of the challenges we are facing when we do tomography. So now. In 20 minutes, I don't have time to make a review of 30 years of global tomography. So I have to make some choice, and I will just remind some basic ideas of how we do global tomography. I wanted to mention some results that are, I think, now accepted in the community, made on global tomography. And I also wanted to say a word on the challenges we are facing and maybe opportunities for the future. So as we all know, we use a seismic wave to sample the deep Earth and the Earth mantle. So it was rapidly shown that at first order the Earth is spherically symmetric, but this is a simplified version of the Earth, and actually the mantle is not homogeneous. We know that it is. There are heterogeneities, so actually the simulation I showed before, the geodynamical simulation, show very well that we expect heterogeneities, but there are some other evidences. Here are just some examples. We have slabs injected at subduction zone into the mantle. We know from geochemistry that there are some reservoirs in the mantle that has been preserved through time, even if there is a mantle convection. So we want to do a better job than a homogeneous model, and this is done with a tomography principle. The idea is you start from a hypothesis, and you do some prediction, and then you compare two observations. And observation has already, I mean, there are many observations you can do. You can make with seismology, so you can measure travel time, you can use the waveform. There are many kinds of observation. And what you do is that you compare then your prediction to this observation, and like that, when there is a mismatch, you can improve your model. And actually, when we do this exercise with enough arrays and cross cross-crossing rate, with a good coverage, you can actually constrain quite well the size and the amplitude of these velocity anomalies. So you end up with a 3D model of seismic velocities that you are all familiar with, like the example here. So when you do the tomographic inversion, it's an inversion, so you start from data and you want to recover the model that could explain this data. So what I really want to emphasize here is the data. And if you don't have data, there is no inverse problem, and I will emphasize a bit later on that. And also, if you want to solve the inverse problem, you actually need to know how to solve the forward problem. So it's to have an idea of the G function that is on the top of the slide. And so for that, there are some assumptions, and we will see that it can make some complexity of the model. So without going too much into the details, here from my point of view, is the 4 ingredients that are extremely important when you do tomography. And as I just said before, the seismic data for me are the most important ones. You are all familiar with seismic data, and I guess we all have our favorite waves, but there are normal modes, surface waves, body waves, and you usually choose the one you need to image the structure you want. As I said before, we need a theory because we need to be able to solve the forward problem to do the inversion, and so this comes with some assumptions and limitations. And finally, last but not least, there is the parametrization, which is how you're going to describe your function on the sphere, so basically cells or continuous function. And this comes also with limitation at the end. And you choose the parameter you want to invert for, so velocity is very popular, but we also, of course, with seismic wave, we are also sensitive to anisotropy, attenuation, so there are different versions of tomography. And the regularization, the damping parameter, I will detail a bit later this parameter, because it's also a big button that we can tune with when we do tomography. So I will not detail the seismic data because I saw here everybody is very familiar with that, but since it is the 40th anniversary of Geoscope, I wanted to of course emphasize that if global tomography exists, it's because this kind of global network has been deployed. So starting with the Geoscope in 1982. And you see here, it's a graph. I just downloaded the list of stations, so it's maybe not the exact curve, but that's what was available. And you see the explosion of the number of stations, and that's really made possible the tomography that we have today with the resolution we reach today. And with lastly, this very dense network that are so yet temporary, but also very useful to constrain the big model. I will just skip that, but I prefer to here come back on this damping parameter I mentioned before, just to explain why we need that. So basically, the problem we are trying to solve when we do global tomography is non-unique. The solution is non-unique. It is underdetermined. We have too few data, even if we have a lot, to constrain all the parameters we want to constrain. And this means that if we want the algorithm to find a solution, we need to kind of help it. And so one way to do that is to start from an a priori model. And so here it's a toy example of the true model, and you start from a homogeneous model, for instance. And you try to recover the truths, of course. And you see that you have a correlation between how the model you will retrieve will explain your data and the damping parameters. Actually, the damping should be the error should be reversed. But the message here is that if you damp a lot, the damping is the parameter that says how far from the a priori model you allow your algorithm to go. So when you damp a lot your model, you will stay as close to the a priori, but you will explain less your data. And when you free a bit the damping, you allow your algorithm to put lots of heterogeneity, sometimes too much. If you go too far in this, you start to have artifacts because you will put stronger heterogeneity at some point, but that will have to be compensated with opposite sign structure if it's not well constrained. So what we try to do actually is to find a good compromise between these two extremes, and generally you want to be in this curve in the corner where you explain well your data and you don't have this too heterogeneous model. So this being said, just now wanted to cite some results about tomography that I guess now are well accepted into the community. I'm sorry I didn't put the figure, but of course one of the, in the very first global tomographic model, Geoscope played a big role, but here the figure I will show are more recent and, as I said, are more from the 2,000 years. So here are these results, the observation of the oceanic lithosphere made from global tomography, where you see very well, if you make an average of the velocity, the shear velocity with the age of the oceanic plate, you see very well the thickening of the lithosphere with the age, and the black line is what is predicted by half-Coolidge space model. So you see, we explain very well what we observe. So this is a very nice observation. And then we can also measure the azimuthal anisotropy. So here the red bars tells you in which direction the seismic waves are propagating in the fast direction. And you can compare that with the absolute plate motion. And when you do that, what you can see in the curve on the bottom right is that you see an alignment of this anisotropy with the APM, so absolute plate motion, for fast-moving plates, so basically for plates moving faster than 4 centimeters per year. And the interpretation of that is that you have an alignment of anisotropic olivine crystals with the plate motion under fast-moving plates. There are also cratons, so we can see them already on the map at 150 with this very fast blue region under the continent, and these are the old continental regions that have been preserved through time. They are really brilliant, and here is an estimation of the thickness, so they can reach 200-250 kilometers thick. And that's also something that is now well accepted. This I can go fast because I guess everybody has these images of subducting, what is interpreted as subducting slabs going into the mantle and stagnating or not at the transition zone. What I would like to say here is that actually in the last years it has been also observed that it's not simply at the transition zone that we might see the slabs stagnating, but maybe below, down to 1,000 kilometer depth. And that's something that has been observed in different tomographic models here. What is shown at the top is the autocorrelogram of a tomographic model. It means you take the tomographic model at one depth and you correlate with itself at different depths. So on the diagonal you have a perfect correlation, of course, because you autocorrelate the same depth, and then you have with different depths. And what is seen on the SAMU CP and SAMU 2 is that you have a decorrelation level at around 1,000 kilometer depth, so where you have the bluish, greenish colors. And this is not seen in the two other models where this decorrelation level is more at the 660. But this has been reported, and geodynamics is trying to explain this, and actually now there is the assumption that it could be due to a decrease of viscosity in this depth range, 60,000 kilometer depth, which could explain maybe a bit this observation. This is more also well known. So these are images I picked for mantle plumes, or at least what is imported as being the trace of mantle plumes. So Montelier et al. Is maybe the first image, from what I know, of a plume. And this one is Widmer-Schnidrig, but we have more recent results of French and Romanovich, where you see this low velocity anomaly starting from the CMB and going up to the surface, right beneath the hotspot volcanoes. And on the last one is a recent image of the La Réunion plume from the Rembrandt project, where you see it can be more complicated. And the interpretation of this is, I guess, is still under discussion with geodynamicists. And here is also very well accepted, the LLSVPs. I think it was one of the first features that was already observed in the first tomographic model. So these low velocity, shear velocity provinces under Pacific and Africa. And the pink circles are the hotspot, and you see that they kind of gather around this LLSVP, so they are maybe anchored at this around these LLSVPs. But what they are made of, or what they are, is still a big debate. So here is maybe a summary figure of comparison of all these tomographic models. The left column is where the model agrees on the high velocity, and the right column is where they agree on the low velocity. And you see that when you do that, so it's a summary from 14 tomographic model. So you see the cratons, everybody agrees at least on that. At 600 km depth, you see more the slabs, or some slabs at least. And you can follow them, for some of them, down to 1500 km depth. And at the CMB, you see that the fast velocity anomalies are around these LLSVPs. And for the slow region, so at 100 km depth, you see that it is correlated with the ridges. It's more difficult to understand the structure in the mid-mantle. And the tomographic model do not really agree on everything. But you see that there are, the improvement of the tomographic model is tremendous. And again, it's thanks to the explosion of the data that are available, and also, of course, the computational power that has significantly increased. So I have here focused only on the shear velocity tomographic model. Of course, there are also models in P velocities that have also improved a lot through time and have reached a similar resolution, but I don't have a figure for the comparison. So this improvement has been really impressive. But there are, I think, still challenges that we are facing in global tomography, and that are definitely needed. When we have just velocity information, when we have BPVS, we can try to make an interpretation on the origin of this velocity anomaly. But if we want to push the interpretation further, we need more parameters. So radial anisotropy is one parameter that would be very interesting to constrain, because it can give us some information about deformation or flow in the mantle. Here is the exact parameter. So here is a summary figure of the exact parameter, which is the ratio between the horizontal shear velocity and the vertical shear velocity. And what you see is that here we have 9 models, and they are really significantly different. It's a postdoc in Lyon who made this figure, Alistair Boyce, and I must be honest, and we were kind of scared when we see that. I didn't know it was that the difference were that strong between the models. So we still need to understand why. And one parameter that is also very interesting and to constrain is attenuation. So attenuation is the fact that seismic waves are losing energy as they propagate, mainly because, so it's not all of that, but part of this attenuation is due to the medium that is dissipating this seismic energy. And we measure that in terms of quality factor. It's the big Q. And the quality factors, if it's big, means that the medium has a good quality as a transmitter, so you don't lose too much energy. But if this Q is small, it's a bad propagator, so you lose a lot of energy. So there are tomographic models of this Q factor, and here is a summary picture of some of them. What you can see is that, again, they don't agree very well between each other. They only exist for the upper mantle, so we still need to extend to the lower mantle. While attenuation is a key parameter, because, for instance, when you have a small slow velocity region, it could be due to an increase of the iron content or an increase of temperature, for instance. And with velocity alone, you cannot really distinguish between these two effects. And with attenuation, because these two, velocity and attenuation, don't have the same sensitivity to thermal anomalies or chemical anomalies, you can try to distinguish between these two hypotheses. So that would be great if we can improve the imaging of attenuation. I don't have a slide, but I could definitely say the same for the density structure, for which we also don't have any consensus on the density structure. And in that context, I find it very interesting to have this initiative in the community, so it's led by Vedlekic and Monique Raj, to build this 3D reference model. So yes, we have reached the point where maybe we could agree together on a reference data set and on a reference 3D model. So it's a hard work, and Raj and Monique is trying to gather the data. So for the surface wave is done, they have published and they succeeded to get a data set, and now they are trying to gather body wave, I think, and at some point from that there will be a reference, 3D reference source model. It's interesting because it can be helpful to start from a 3D reference model than to start with the usual 1D model when we do tomography, or it can give you a better a priori model for a later inversion. So, and I just wanted also to mention that there has been a big effort also of the tomographer community to make this model available, and IRIS ENC is a project that where all the Earth models are gathered. So as soon as you publish it, you can send it to IRIS, and they will make it available with the same format for all the models. So it's simplified the plotting afterward. And also there are some other initiatives to try to provide to the community tools to help for the visualization of this model. So Tomopy is a Python application and interface that I developed myself, and Submachine is from the Oxford group. It's more a web application, but where you can also play and with the models and just plot them and do some statistics also. I wanted to finish on some maybe opportunities for the future in global tomography. There are not all of them. Maybe here again I am biased by my own research, but I found interesting from since 20 years that there is this development of ambient seismic noise cross-correlation, where they have shown that by cross-correlating the noise recorded at two stations, you can get the green function. So you can be in a situation where your station is like a virtual source and recorded at the other station. And this is very nice because you can have a new coverage of the mantle because you use only station. And there are actually regions of the mantle that could maybe easily covered by this kind of data. But I know that it's also difficult to produce this kind of data, but it could be a good opportunity for tomography. I also mentioned here rotational sensors that have been deployed, developed, which now can record the rotational motion after an earthquake. And here are just some examples where, so you have, I think, in black the rotational signal, and you see that we are able to compare to a usual translational sensor, and you see that we see body waves. So we still need to understand these recordings, but that's also maybe a good opportunity for tomography in the future to have new data and to constrain the mantle structure. There are other data, I cannot mention everything here, but so just to say that there is many things to be done in the future. The last point is more a methodological development, but we could also try to improve the way we make the inversion. There is a Bayesian approach that allows to explore all the models, but it's very expensive, so at the moment it's not really feasible to do that at the global scale, but maybe in some years it will be. So I just would like to conclude by acknowledging that Geoscope was definitely a starting point to make global tomography, even so I was very young and I did not see that. And but definitely today our job is made easier because all these projects have started, and I hope it will of course continue in the future. Thank you.
Thank you very much. We have time for questions.
Hello. Your difference in models that you showed and this ray density plot sort of brings up the question of how much work has been done in characterizing errors in the models, and especially with regard to the spatial errors that might be different across the globe because of uneven station coverage, and do you think we might use some of that type of analysis to actually drive the case for where we might install new global stations?
Yes, very good point. So tomographers like to avoid to talk about uncertainties, but that's why Bayesian approach actually will solve a bit this problem, because it's unable to take into account these uncertainties. There are two problems. It depends the way you do your tomography. But if you want to have the uncertainties, you need to compute the a posteriori error matrix. And this is expensive, and you don't always do that. And even when you have it, it's difficult to represent it or to exploit it. So we could give some range of uncertainty from that, but it would be difficult to really to make it meaningful, maybe. And for the spatial uncertainty, so we always look, we still try to account for that doing synthetic tests, basically, where we check if our ray coverage allows to recover the kind of heterogeneities we are seeing. But it's true that it's more qualitative than quantitative, I would say, at the moment. And that's really something that should be worked in the future.
There's another question.
Okay, thank you for your presentation. My question is also about Bayesian approach. Actually, I find that this comparison of different models is kind of first iteration of this. Yes, where you take, for example, 16 different models, and it's some kind of a posteriori estimation. So I agree that this is maybe not feasible to do a full uncertainty estimation, but maybe this idea to check some particular interesting features, if they are persistent or not in the models, can this be done in feasible future with this Bayesian approach?
Yeah, it's a good point how you say it. I guess it could be a first step to try to go in that direction. I'm not a specialist of Bayesian approach, so I'm sorry I won't be able to tell you more. But if maybe somebody has something to say, or
we can discuss that later. We have to move on now, looking at the clock. Our next speaker is going to talk about normal modes of the Earth, and he's going to show us some selected observational aspects. Widmer-Schnidrig, please, the floor is yours.
Hello everybody. I like a challenge to talk about normal modes in just 15 minutes. It's a field that started in 1960, so it's 42 years ago, 62 years ago. And upfront I want to acknowledge my colleagues from the Black Forest Observatory in Barruol, and who is not here, but they send regards to all of Geoscope, very heartfelt regards, and he's well and doing research every day. He just came out with Kobe and Thomas Vorbeger. Many ideas in the later part of the talk I've developed together with members. Yes, so normal modes. What is the promise of normal modes? And while, as we've seen in the previous talk, travel time tomography can perfectly image velocity heterogeneity in the Earth and velocity distribution on a 1D spherical average scale. Normal modes have the potential to illuminate density, and this is going to be what I'm focused in this talk, and how does, after 62 years of normal mode seismology, what is the state of knowledge in terms of density structure? And one paper, and let's see, that's the first two parts, and then I go and look at what is the path forward, yes, because not all is perfect in terms of imaging density structure. A paper that has very well summarized the state of 1D density structure is the one by Masters and Gavins in PEPI in 2003, where they did a classical backoscaler type resolution analysis. And on the left you see an overview of the data that they used. They use all the degenerate frequency up to 10 millihertz. So the lower half of this dispersion diagram. And on the right you see resolution kernels. And when you do backoscaler inverse resolution analysis, then you can choose an error with which you want to know a certain property. And it gives you back a width, an averaging width over which you have to average to get this kind of error. So if you want a small error, you have to average over a large volume. And if you want, if you can settle with a large error, then you can make very narrow averages. And the plot on the right shows these averaging kernels for different depths. And the three parameters in this resolution analysis are P wave velocity, S wave velocity, and density. And P and S wave velocity kernels are straight line, flat. The normal mode data has been it has been concentrated in narrow kernels. So these kernels for different depths are narrows near the surface. We have most mode data sensing the top layers in the mantle. And then as you go deeper down into the inner core even, then these kernels get wider. So these kernels and the errors that we can play with there are good enough to answer important questions in Earth structure, like the density jump at the inner core boundary, or is the D double prime is associated with the density heterogeneity or not. So this, I think this is quite a good state for 1D spherical symmetric density structure. I said they use the data up to 10 millihertz. The colored dots in the dispersion diagram between 10 and 20 millihertz, I've obtained those with so-called multiple stripping, a linear technique to estimate multiple resonance functions from observed spectra. And the purpose of showing this here is just to say that there's plenty of signal up there in the band between 10 and 20 millihertz. And if you want to improve on the density resolution in 1D, we have to add those modes at higher frequencies. They have short radial wavelengths. If you add those, if you build linear averages of those mode kernels, you can get narrow averages. That's the way forward. However, to isolate those modes, it's quite a challenge, theoretically, and also in terms of data coverage of the globe. So you have to live with the fact currently that there's large bias in this data set, and so I only plot the symbols because I detected the mode, but I don't trust these values because I have no clue or no handle on how large the bias is on these frequency estimates in the dispersion diagrams above 10 millihertz. Okay. This problem of one problem that you have in a heterogeneous Earth is that modes couple, and in a thesis submitted this year by Widmer-Schnidrig at Utrecht, he looked at the radial mode overtones which go down into the inner core, and he used different theories. That's also an important point from the last talk. You have to have the right theory, and theories have evolved and gotten more elaborate recently to do these measurements. And you see you have a different systematic bias between the red and the black dots. Either in one case you don't include multiple coupling, and in the other case you do include it. And this is a picture from Simon up to 10 millihertz. And if you look on the far right, you see that I was actually able to isolate radial modes up to 20 millihertz. So a mode like 21 S0, the 21st overtone of the radial mode, it is going right down into the inner core. That's well, a clear signal, and I'm very enthusiastic, very positive that sooner or later this mode will be able to measure the degenerate frequency and be able to account for coupling with nearby modes. If you look at other resonant spectra of these multiple strips, they're called, of these modes, you see that there's multiple peaks, and this is exactly the issue. You have nearby modes with which these radial modes couple, and this leads to bias, and you don't want to have bias data in your inversions. Okay. Another view on the data, so just for the path forward, these mode branches in the dispersion diagram, they extend out to 18 millihertz at least, some up to 20 millihertz, and I've only shown here all the multiplets for the 7th overtone and the 23rd overtone, the 7th overtone on the left, plotted relative to the predicted frequency of CREM. So this multiplet stripping, which is the most simple way of isolating mode, works all the way up to the highest frequencies, and we see a little deviation away from CREM. The zero line should be CREM, where all the spectra align. But it's hard to say whether we have a bias in this data set due to uneven distribution of quakes and uneven distribution of stations, or whether this is a real deviation that the Earth is actually, average Earth is slightly different from what CREM is telling us here. The same on the right with the 23rd overtone. So there are modes close to 20 millihertz which we can isolate. They have a clean resonance function. And the signal is there, it's just waiting to be analyzed. But we definitely have to go with the theory to include all the modes that couple in there. And there are very many modes coupling there. Okay. Let's go to 3D. With 3D density, it has already been mentioned in the previous talk. There is an ongoing debate, to say it mildly, if the data, the normal mode data, can or cannot have enough signal, it can resolve density heterogeneities independent of P and S wave velocity heterogeneities. There's one publication in Science in 1999 where this was advocated that it's possible, and Barbara and Guy Masters shortly thereafter countered and put a big question mark behind these models of 3D density. And from a theoretical point of view, Rafi and co-authors looked at the influence of using a simple theory of isolated modes versus wideband coupling, and they find that unless you do wideband coupling, your signal from 3D density is you will lose the signal from 3D density in the theoretical inaccuracies. So the signal from 3D density is as large as the difference between uncoupled and wideband coupled synthetic seismograms. So there is, I guess if I have to summarize this state, the signal is very close to the limit of detectability, and we definitely need wideband coupling. Now, I'm not an expert in wideband coupling, and that's very demanding computationally and theoretically as well. And I still, in the work at the Black Forest Observatory, we still think about a lot about the path forward. And this point was the signal is at the limit of detectability. Well, how can you improve the signal-to-noise ratio? And that's where these three bottom questions come from. Do we need different sensors? Do we need better seismometers? And can we better understand where the noise comes from in our seismic data and reduce that? And this is the point I want to elaborate in the rest of the talk. Different sensors, yes, at the very low frequency end, there are sensors which are better than seismometers, and superconducting gravimeters actually have an edge over STS-1 seismometers. They don't have an edge in price, but certainly they have an edge in performance. Below 1 millihertz, they outperform STS-1 vertical component seismometers when you apply an atmospheric pressure correction. And here we have the multi-taper spectra of the mode 0S2, and you really have plenty of signal to get a very precise estimate of the spectra here. So that's wonderful. Wavelength of 0S2 is very large, 20,000 kilometers. We don't need a dense network for 0S2, and I think the global network of superconducting gravimeters is just fine to address these modes here. So I wouldn't propose Geoscope to get an SG gravimeter. Different sensors. Here I look at the strain meter. You've heard lots of complaints already about how much noisier horizontal components are relative to vertical components. Now, strain meters also sense horizontal motions, differential horizontal motions, but they don't suffer from tilt. And so here is an image of the displacement field of the McQuarrie-Rice event. First time I saw 0T2 in the data, and you saw the animation. And on the right, you see at the bottom the Streckheisen STS-1 seismometers, and I have to say these are some of the finest horizontal recordings in the GSM. And still, you don't see 0T2 in there. However, in the strain above, you see 0T2, you also see 2S1, and the one thing I would like to point out here is that this is the only recording where I see splitting of toroidal modes in a single spectrum. So that the strain meters have actually managed this feat. But as soon as you go to higher frequencies, 1 hertz and above, strain meters no longer compete with seismometers, so I don't think we should deploy a large array of strain meters globally, though that's my view right now. Vertical components, there is, if you compare the different STS-6A, the Trillium 360, and the STS-1 in a Hubble test, and they're almost, and at the quiet side, they almost perform equally well. It's just in this mini room around 3 millihertz, where you can see that actually the STS-1, and this was done in 2020, in a large Hubble test at the Black Forest Observatory, we still see that the vertical component STS-1 has lower self-noise. The PSD of these 4 days of data is just lower. These little circles indicate the PSD of the STS-1. Everywhere else, you would say, without doing any pressure correction, these are raw data spectra. The instruments are comparable, and you don't lose much. However, if you try to apply pressure correction, we find that the STS-1 is still, it works better, this pressure correction, than for other sensors. So self-noise is closer to ambient noise for STS-6s, Trillium seismometers, than for the STS-1. So there's a little bit to be gained if we had instruments like the STS-1 for the future. Then, do we need better insulation techniques? And this is an experiment we did at BFO with lots of support from Albuquerque, from Adam Ringler, who came with a technician. And he helped us drill a 1.60 meter deep hole, deep in the mine, 150 meters below the surface. This is the lower left sketch, where we have installed a post hole. And up to that point, I was convinced that we have very good and very low noise horizontal component seismometers, the STS1 and the STS2, which I sketched on the right. And then you install the post holes, the STS6 is the post hole, and you drop another 7 decibels on the north-south component, at least 3 or 4 decibels on the east-west component. So this really surprised me, and I think there's a number. When you go from one installation to the other, you change at least about 3 things. I think the seismometers are equally very close in quality, equally good horizontal, certainly. But one thing that we did not only go to the post hole, but we placed the post hole on the symmetry axis of the tunnel in which this is installed, and going away from the walls on the side and going right in the middle where the symmetry axis is, I think is largely responsible for this difference between horizontal noise spectra from wall seismometers and post hole seismometers. So it's something to take along for other installations. If you have a choice, definitely suggest going into a symmetry point to sense the least amount of cavity effects, as they are called. Do we need better shielding? Now this is an experiment that was triggered by an observation of an eclipse on the surface of Mars. So I am fortunate to be a member of the Inside Science team, and when we got the data down from the Phobos eclipse, when we knew that there would be an eclipse, and we were puzzled certainly, and intrigued by the data, and that eclipse on Phobos takes 28 to 30 seconds. That's a very rapid event, and Phobos flies really low, and so you just imagine you turn off the light for 30 seconds, and you get the tilt signal, which you see at the top left, the seismometer tilted away from the lander, and this tilt started within about 7-8 seconds of the onset of the eclipse. Or it was only transit, the sun didn't get fully eclipsed. And I have recalled that my colleague at BFO, Walter Zurn, did experiments of thermalistic experiments in the mine. And then the next day after this science team meeting where we got this data, I was in the mine experimenting with a 100-watt light bulb and an STS2 seismometer. And I was just trying to understand, is turning on a light bulb next to a perfectly shielded STS2 seismometer on a pier, and I maintain that the DDE seismometer on Mars is a perfectly thermally shielded seismometer. It has a thermal time constant of close to 3 hours. So how would that go on Earth? And I was really surprised that indeed, if you turn on the light, either the light bulb on the pier or the light bulb on the ceiling, you can see a tilt response within 10 seconds. And this seismometer that's on the image is rather poorly insulated. I added more styrofoam insulation and to protect the seismometer from direct irradiation. So it's all through the heating of the top 1 millimeter of the pier, or the top 1 millimeter of the regolith on Mars, and its contraction or expansion due to the missing heat on Mars and the input of heat on the pier, that the seismometer starts tilting. And what I learned from this is that it's maybe worthwhile to think one more time about shielding, not only of seismometers, and thermal shielding is certainly important, but also shielding of the pillar on which these instruments are installed, because of this thermoelastic effect. And then the point about better understanding pressure-induced horizontal acceleration noise. I mean, the atmosphere is a complex beast, but you can try to start with very simplistic models of plane waves propagated through the atmosphere. And here I've drawn a pressure wave in the upper diagram on the left, and below the response of a half space, and in this half space is a seismometer vault. And if you look at the lower left picture, pressure is maximum, the surface gets indented, And if you apply pressure to a half space and you have a cavity in there, then the floor warps upwards, the ceiling warps downwards, and if you have a seismometer on the left and on the right of this cavity, it will tilt away, and they will tilt in opposite directions. And it's just what you see in the north-south panel on the right, that we have two seismometers in our seismometer vault, and the signals are almost perfectly flipped. Simply because they stand on opposite side of a vault, and at the bottom trace we have a pressure wave propagating over the Black Forest Observatory in the bottom trace. Then if you have a gradient in pressure across the Black Forest Observatory, regional pressure gradient, then the whole cavity, the whole mountain tilts, and also the chamber within the mountain, and both instruments see the same kind of tilt. And this tilt is in 90 degrees out of phase with the pressure signal, whereas on the bottom left, first the deformation of the cavity, there the tilting is in phase with the pressure. So you have two responses, one where the tilting is in phase with the pressure, and one where the tilting is 90 degrees out of phase. And it goes on as you move on to this pressure cycle. And so we come up with this model of trying to model the horizontal acceleration, AH, as a linear combination of two pressure signals, the scale version of the direct pressure measured above the vault, and a second scale version of the Hilbert transform, which is 90 degrees out of phase with the pressure. And with that, and this is work in progress, there's one publication mentioned at the bottom, we try to come up with better ways of removing this really large signal that you see on the right in our horizontal components. So these are where we go with our concepts to try to improve on the observational side of. I said in the second position where the whole chamber is tilted, you need a gradient. Typically at the seismic observatories we only have one barometer, and so one obvious thing to do is to take a MEMS barometer, develop a known data logger for that, and in Erhard's addition, do it yourself and in the lab. So I stuck this together. And we deployed 20 of these MEMS barometers around the Black Forest Observatory. Right, you see the traces. When a cold front passes, comes from France and moves westwards, moves eastward. And when you put this all together on a wave field plot, an animated wave field plot, and these are bandpass filtered barograms, then I show you just two snapshots, not the movie, but you see at the bottom left, you see the barogram, and the vertical bar shows the point in time for which the snapshot at the top is plotted. Early on, when this cold front moves across the observatory, you have coherent wave field, and you see a steady gradient across the wave field, across the array, from bottom left to top right. It should be very encouraging. Yes, we can capture the gradient with this array, but further down, the coherence breaks down, and I think the wind has picked up, and our barometers show complete incoherent signals. So it's a tough situation we're facing here. And this was a tiny array, 5 kilometer aperture, and I want to conclude with a look at the global array of barometers, because this is a talk on low mode. You see that from the Hungatonga event, the land waves propagating around the globe and traveling at least 4 times around the globe. And on some traces, you see that the waveforms basically don't change from wave packet to wave packet, they just get smaller. So you have basically no dispersion, and group velocity is equal to phase velocity. You have a velocity of like 330 meters per second, and you can predict what you get when you Fourier transform these traces. And to convince you that these are the normal modes of the atmosphere that you see in the lower right, I did twice the same analysis, one with a love wave seismogram from the Balani earthquake. You see periodic love waves which come back to your station every 2.5 hours, because they you travel around the globe with this, take these 2.5 hours, and the mode spacing, asymptotic mode spacing of fundamental toroidal modes is 1 over 2.5 hours or 111 microhertz, and this is a spacing that you see in the frequency plot below. If you go to the right, you keep the seismogram more or less. You just change the axis. The time axis is now 7 days long. The orbit takes 35 hours, 35.5 hours for one orbit around the globe. 1 over 35.5 hours is 7.8 microhertz. You do a honey taper and an FFT, and here you see the normal modes of the atmosphere of the Earth excited by Hunga Tonga and recorded at Tamanrasset in this case. So, well done, Geoscope. Nice barometry. And with that, I would like to conclude. Yes. 1C density, we're in very good shape with 3D density. This is where we have to work on in the future, because this, for the geodynamics, it's absolutely essential to know 3D density. It drives anti-convection. And yes, we need to improve observations. I've sketched a few paths forward, and on the theoretical side, we definitely need to implement wideband coupling to get better 3D density. And Geoscope has made a very essential contribution to the data set, which is at the bottom of all these observations. A French seismometer is currently operating on the surface of Mars, and I don't see why Geoscope should not expand beyond the Earth in the decades to come. Thank you, Geoscope.
Thank you, Rudy. We have time for a very short question.
About attenuation, and I was just wondering if you think getting a 3D attenuation model of the lower mantle is probably very important too, and I was wondering if you think that there is a potential with nanotubes to constrain the 3D attenuation of the lower.
Yes. There's a chance, but it's Barbara should answer this, yes.
No.
You have worked a lot on attenuation, yes. It's also a challenge, yes.
There are some theses right now at Utrecht on that subject.
Yes.
Yes, quite a few.
I have a question.
Okay, very quick question, Barbara,
So,
and then we change it.
also about density, 3D density. There is now a new technique based on using tides,
Yes.
which has just added fuel to the controversy about whether the LSVPs are denser or lighter. What do you think of that?
I didn't follow it that closely, yes. No, I will not comment on this one.
Okay, thank you very much. That was a very short reply. Now we are going into the core. 40 years of core studies for broadband data by Souriau, Calvet, and I see the talk is going to be given by Anita.
Thank you. So, I show you the core as we represented in the 19th century. The core as it was 40 years ago, and the core now. So, I will mostly comment the difference between these two images. And in fact, the difference mostly comes from the availability of broadband data with a worldwide distribution. I will not explain in detail how we obtain this model because it would take a long time, but just what I would like to do is first to present the model and then to give to show some reports which illustrates this feature of these models, or some of them which even reveal some feature of these models. So, here is the core as it is, well, roughly it's the core as it is described now. There is core mantle boundary and inner core boundary, which both are considered as first order discontinuities. The liquid core, which is in fact it's molten iron but not pure. It includes light elements, mostly sulfur and oxygen. It has a low viscosity, like more or less the viscosity of water at the ambient temperature, and because of that, it is well mixed, so it is homogeneous, except a basal layer which is denser. Now, the solid inner core, it formed from the crystallization of the liquid core, so it is rather long, probably less than 1 gigabit. It is considered as almost pure iron, so that it's depleted in light elements, and during crystallization the light elements go away. It is globally anisotropic, with a fast axis parallel to Earth's rotation axis for velocities, and this axis is also an axis of high attenuation. The attenuation, the anisotropy is different in the center, it's what we call the innermost inner core. Also, the anisotropy is different in the external part of the core, it's very low. So often this layer is considered as isotropic. And finally, not finally, but almost finally, there is a dichotomy between western and eastern hemisphere. These two hemispheres do not have the same structure. And concerning attenuation and velocity, the variations are in opposite sign compared to the mantle. So what are the tools we have? First, the normal modes we were speaking about. What is interesting for the core is that the normal modes give access to the globality of the core, and they detect the shear velocity, which is really difficult to see with body waves. So, in particular modes, it is evident that the inner core is rigid. Also, they allow to reach the density of the liquid core, and it's a strong, they give strong arguments in favor of the fact that light elements must be included in the liquid core. Okay, I show you here 3 modes, and you see the sensitivity to the density to the left, to the P and S velocity to the right, and to this at this mode, which are selected because they are core modes, have energy. For example, this one is the density in the inner core, that one P velocity in the inner core. And I will later come back to this model. Body waves, you have a lot of body waves, which are transmitted, reflected above the discontinuities, reflected below the discontinuities. Some of them turn in the upper part of the liquid core, some of them in the base of the liquid core, some of them in the inner core. And usually, because the core is hidden by the mantle, it is usually we use comparison between a wave which turns in the inner core, for example, and a wave which turns inside the liquid core. Well, most of the studies use rather simple approaches using travel times, amplitudes, really classical things. Okay, so scattered waves, there are of course also body waves, but because they do not follow the ballistic propagation, they are not modeled in the same way. Usually they are modeled as with equation of diffusion, and they give information about the texture, in particular of the inner core. Okay, now I will show, as I told you, some records which illustrate all these features. I'll start with the core mantle boundary and the liquid core. And here is a beautiful figure from my colleague from Potsdam, where you see on the left this path, PK, IKP in green, and the path in red, where you just add 4 legs inside the liquid core and 4 reflections beneath the core mantle boundary. If you observe the records, so for the single wave and for the 5 PK, 5 KP, you observe that you still see the wave. So it has not been strongly attenuated. But what you see also is in this record of Black Forest is a shape similarity between PKP and P5K. And this demonstrates, this simple observation demonstrates many things. First, that the liquid has a high quality factor. You are still able to see the wave after a long pass. Then, it's not strong lateral heterogeneity inside the liquid core, else you would lose the phase. Then, concerning the core mantle boundary, it shows you that it is a first order discontinuity, else you will have reverberation and change the shape of the wave. It shows you that the reflection coefficient is high, else you would lose the phase. And finally, it tells you that there is no strong topography at the core mantle boundary, else you will also distort the phase. So you see that a simple observation contains, in fact, a lot of information. Now, looking at the base of the liquid core, I told you the results here, we will consider this path here, PKP-BC, which corresponds to a wave which samples the base of the liquid core. This wave is well observed here. It's a very clear wave, but which is observed only in a rather short interval of distance. Looking at the time arrival at this wave compared to Prum is here, and here you see that at some distance, this wave departs significantly from Prum. Prum is an interesting model for that because it's a model which is built for following Adams-Williamson equation, which means that it's stable in stratification. If you take a piece of Prum and you displace it, it will stay where you put it. So it's a stable structure. This curve needs to have a decrease in P velocity. So you must depart from a stable stratification. And a decrease in P corresponds to an increase in density. So you clearly have a layer with an increase in density at the base of the liquid core. And this has important consequences because, as I told you, the inner core crystallized from the liquid core. So if you have this layer at the base, it's kind of shield which prevents the exchanges between the liquid core and the inner core. So how to explain it? Possibly because there has been a refreezing of the inner core, and because the inner core was depleted in light elements, it gives a melt which is also depleted in light elements. Or another possibility is that this layer was pre-existing, I mean that it was a primordial structure which formed during the differentiation of the Earth at the very beginning when the Earth differentiated. So it's an interesting feature. Now the solid core. Again, I show you this mode. 13S2, which has energy here, P energy in the inner core. At the top is a record of this, of the Bolivian, excuse me, Here you see a maximum at about 600 kilometers for P, which means that with an earthquake at 600 kilometer depth, it will well excite this node. So here is the record of the Bolivian earthquake from 1994, which was a big earthquake, recorded at the Arta Observatory at Djibouti. You see the 15 first hours, and the continuing of this record is vertical. And here, the same filtered around the frequency of 13 seconds. So you see you have a lot of signal, even 100 hours after the beginning of the earthquake. Here are the modes, here are the peak of 13S2 at different stations. And finally, here is a splitting function of this mode, not only for this earthquake, but for a stack of several earthquakes. And what is absolutely clear is that you have a latitudinal pattern, which has been interpreted as due to anisotropy inside the inner core. So you have an anisotropy with a fast axis parallel to Earth's rotation axis. This is also clear from body waves. Here you have some records, which all correspond to the same epicentral distance, to the same region turning for the turning point, but which correspond to various orientations. Some are parallel to Earth's rotation axis, others are parallel to equatorial plane. And if you consider the different records, here the phase with the black dot is the phase inside the liquid, and the one with the red dot is inside the inner core. You observe that for paths parallel to Earth's rotation axis, the phase for the inner core arrives much earlier than if the path is parallel to equatorial plane. Also, you see that the amplitude ratio is much smaller. The amplitude ratio between PKPDF and PKPPC is much smaller for paths parallel to Earth's rotation axis. So you have a clear evidence of anisotropy, at least between this region which is inside the field. And we observe that the fast axis and the high attenuation axis are parallel, which is a correlation opposite to that which is observed in the mantle, where we have generally high velocities which correspond to a high quality factor. Okay. Now I will show this record and this record at different frequencies. Just to have an idea of the explanation of this anisotropy. Because what we think about this anisotropy is that it could be due to a preferred orientation of crystals, but also it could be due, for example, to preferred orientation of fluid pockets. In any case, it's supposed to be related to a problem of texture. So if we consider these two records at different periods, here is the path parallel to the equatorial plane, and here the path parallel to the rotation axis at different frequencies. You observe here, for example, that the amplitude ratio between DF and BC is unchanged with frequency, and here that it collapses when the frequency increases. Here DF is multiplied by 10, and even so it's difficult to observe. So this is a strong argument in favor of an explanation by a texture inside the inner core. Okay, let's come to the velocity. This figure is due to my Japanese colleague Tanaka and Kunobushi, where it's absolutely clear, it's travel time anomalies, that the eastern and western hemisphere are different, both for polar paths and for equatorial paths, I think it doesn't need any comment, it's very clear. Just to notice, however, that the amplitude is not the same for equatorial path and polar path, but it clearly shows a dichotomy with an eastern hemisphere which is fast for polar path and slow for equatorial path, and the opposite with slow for, sorry. Yes, so a western hemisphere which is fast for polar path and slow for equatorial path, okay, and the opposite for the other hemisphere. How to, well, interpretation are still debated in fact. It could be due to, for example, different thickness of the isotropic layer, or to some disorientation of the crystals, or to different texture, which could be, for example, difficult to detect with waves which are parallel to the surface. But this has still to be modeled. Now we come to the isotropic layer, where we observe exactly the same thing. Looking at these two waves, which are one reflected, one transmitted at the inner core boundary, it's clear from this figure from Ben and Moon that the time difference here is larger than here. And as plotted in this figure by Calvet and Romanovich, we again clearly see the dichotomy between eastern and western hemisphere, both for peak velocity and attenuation. It's hard to explain. It's hard to explain because we have the idea that, in particular for such deep structure, everything could be controlled by sphericity or by Earth rotation. And in fact, no. One of the possibilities is that there is a forcing of the crystallization at the surface of the inner core due to the thermal heterogeneities which are controlled by the core mantle boundary. So the core mantle boundary is thermally heterogeneous. It induces some currents inside the liquid core which force the crystallization to preferentially occur at some places. Another possibility is due to a mode of convection inside the inner core, which in fact results in a translation of the inner core, so that because the surface of the inner core is at the freezing point, you have permanently freezing in one side and crystallization on the other side. And this makes that the core is permanently moving. The origin could be possibly a thermal origin, but more likely a chemical origin. Finally, one slide about the scatters. Scatters are difficult to observe because they require to be stacked, in fact, on a small aperture array. So you see here, for example, at the top, the Central American earthquake recorded at Hailey Edison Array in Alaska. At the distance which is considered, the reflected wave, KKI, disappears. I mean, the reflection coefficient is close to 0. But nevertheless, you see a coda which is here, it's to this. And this coda corresponds to waves which are scattered inside the inner core just after this arrival of PK with the IK. What is interesting is that, for example, if you could compare these two pictures, you have stacks here for the same array in Alaska, and here for Yellowknife in Canada. Here you have a coda, which is like this spiral tail, which denotes that scatters must be rather deep. Here you have an image which starts rather steeply before having again this tail. And the fact that you have energy rather steep here denotes that numerous scatters which are very close to the surface. So in two regions which are not extremely far from each other, Alaska and Canada, you see that you have texture inside the inner core which are not the same. So this certainly has to be investigated further, but as I told you, you need smaller aperture, so it's not extremely easy to do some systematic studies about that. Okay, to conclude, first, it's clear that there has been a great contribution of broadband data to the knowledge of the core, in particular Geoscope, with very interesting location of stations. That for core studies, there is still a promising future, because as I told you, there's many unsolved problems, in particular concerning the texture, concerning the anisotropy, and there is also a lot of work to do for the modeling, in particular this problem of hemisphericity. We hope to have, with new observational approaches, some new information about the core. But I hope, well, I should be this PKP observed from the ambient noise, the group of phenomena, so it's rather promising. But first, it's important to continue to look at individual data. I hope I convinced you that in single records you have a lot of information which give a lot of new ideas. So, in addition, it's fun. So, really, it's important to continue to look at data. Also, it's, in my opinion, extremely important to continue to collect data and unstable networks. So, if you want to do some seismology which is independent, you need to have some stable instruments. Okay, that's all.
Thank you very much, Andy. Is there a question? Yeah, Frédéric?
In all these core studies, you always show rays.
Yes.
But what is the Fresnel zone of these things, and what can you expect actually to see with your waves?
Well, the Fresnel zone, in particular in the inner core, is very large. It's, for example, for a PKP at 2-second period, the Fresnel zone is almost one-third of the radius of the inner core, so it's very large. In fact, right now we have not worked a lot, except a few papers with this, taking into account the Fresnel zone. We have mostly worked with differential travel times, which partly remove this problem, but not all, not completely. So I think there is still a lot of things to do with that. But it's difficult. It's difficult. What is difficult is to have really high frequencies, to have small Fresnel zones. Because if you have a Fresnel zone which is too large, it loses some interest. You see all the inner core at the same time, so it's not.
Thank you. I would say seismology is like difficulty, and that is why we are where we are. I think we have to move on. Sorry, Jean.
It's too late.
Yeah, let's move on. We are already running late. Tina Thomas is going to talk about the structure of the D double triangle.
Okay, thank you very much, and thank you for the organizers to put together this really nice program. I was asked to talk on the structure of the D-double prime region, and then Barbara said in the next line, but you only have 20 minutes. So that's of course quite difficult, because just as normal modes and so on, D-double prime has been looked at for a long time. So we have the mantle and we have the core, and now we're going to the region between the mantle and core, the core mantle boundary, the D-double prime region. And at this area we have an interaction between mantle and core through heat, mass, and momentum. But the Lomos mantle is really affected by the processes that we have in the mantle, but also by the mineralogy in the mantle, and I will come back to that later. So if we have processes in the mantle such as convection, and we have mantle mineralogy, for example, bridgemanite, which was used to be called perovskite and post-perovskite, then we have a boundary layer, and we will generate a large number of structures. And you can see here, for example, the large low seismic velocity provinces, ultra-low velocity zones, but also it might be the resting place of slabs and the starting place of plumes, and also there's a lot of scattering apparently in the low mantle. So it is a very heterogeneous region, and because there's far too much to talk about in 20 minutes, I will only focus on the D-double prime reflector and the area below the reflector. So looking at the D-double prime reflector, it was first observed, well, there was actually evidence for a difference in velocity structure already in the 60s, but then in 1983, Ley and Helmerger found observations, or found waves arriving between the S wave and the core reflection SCS. I have a picture up there of P and PCP, but it's the same for the S waves. And they went out to model this reflection with a layer on the far over there, with a layer about 300 kilometers above the core mantle boundary. And you could sort of reproduce that reflection that we see. Later, we looked at the same reflection with P waves, and you can see at the bottom there an example of the P wave. The data are aligned on the P wave, and what we have in there is the Greifenberg array and the German regional seismic network, and then a very large amplitude reflection that I call PDP, and then PCP, which is hardly visible. Quite often, we use arrays and networks to detect the seismic wave. We do this in often stacking a number of seismic recordings. And what I've shown there is we have an arriving waveform, the green wiggles there, and then if we stack along the blue or red lines, then we either add up the wiggles, as in the red case, in the red line case, or if we stack along one of those blue lines, we will have a much smaller signal. So using that, we can actually determine the angle of incidence that the wave has at the array, which also helps us to distinguish between different waves. So as you can see in the figure on the left, the P wave has an angle of incidence that is, well, if you look from the vertical, that is larger than the PCP wave that comes closer to the vertical. And PDP, the reflection of the D-double prime layer, comes somewhere in the middle. So we can use the slowness or angle of incidence to differentiate between the different arrivals, and then we can start and search for those. What we usually do is we use the travel times between either the PCP and the PDP wave, or SCS and SDS wave, or the travel time between the P and the PDP, or S and SDS wave, to determine the depth of the reflector. But we can also use the amplitude of this reflection, which gives you an indication of the velocity contrast across the reflector, of course. Then you can look at polarity information of this reflection, and also waveform. The polarity determines or tells you something about whether it's a velocity increase or a velocity decrease, whereas a complexity may be some sort of layering, for example. And the last thing that people start using is the frequency content of these seismic waves. areas, but that's a bit more difficult. But it would give you maybe an indication of the sharpness or the size of the reflector you see. So using all this information, or using especially the travel times, we have detected quite a number of reflections of the D-double-prime layer in several regions, and this is a compilation. There's lots of different studies in there. In green, there's the S-wave reflections, in blue, the P-wave reflections, and they're superimposed on these vote maps, which stack a number of tomographic models. And as you can see already, the vote maps are quite different. Also so we have the S-wave vote map on the left and the P-wave vote map on the right. But what you can see is that many of these reflections have been found in these high velocity regions. And I've actually stuck here the high velocities. So there's many more S-wave observations than P-wave observations currently. And these stars show areas where we really have looked for the double-prime reflections and we cannot find them. I have to say for that some of these have very short distance paths, so sources and receivers are very close, and the reflection coefficient for P-wave reflections is then very small. So possibly we can't see them because they're buried in noise. So you have to keep that in mind. So we seem to have reflections mostly in high velocity regions, but we also have some reflections in low velocity regions, especially there in the Pacific, but also in the Indian Ocean. Then when we look at this reflector in more detail using the travel times, then you can see that some of these reflectors or some areas seem to have very large topography. So up there is one in Eurasia, the reflector beneath Eurasia. On the other side is one beneath the Caribbean. Down here is also the Caribbean. And so apparently there's very large topography. And also in some regions a second reflector a little bit further towards the Coromandel boundary has been detected, which seems to have less topography. So there's a number of publications that show that. There's actually also a publication that shows up to 4 reflectors in the Pacific, but they're possibly due to a different cause. The other thing that I find very interesting is that when you actually look at these reflections and you're trying to look at the amplitudes of the reflections compared to either the P wave or the PCP wave, you find a huge difference between them. So at the top there is something that I would call a normal PDP. Then the second one, the 17th December, is a very large reflection. And then the 12th of November 03, there's nothing. We can't find anything. So it might be buried in noise, but the distance between all these different ones is the same. So you have very similar distances, so you should really have the same reflection. And then at the bottom I've showed an SDS wave as well, so an S wave reflection. If we interpret this amplitude as a velocity contrast, then we usually find something like between 1% and 3%, but actually regionally there's some evidence for about 5% velocity contrast across the D-double-prime reflector. Smaller than 1%, I think, is probably often buried in noise and we might not be able to see. The other interesting thing is that P waves, they usually have smaller amplitudes than S waves, the P wave reflections than S wave reflections, which could contribute to the fewer P wave observations that we saw in the other field. But one other interesting thing is that sometimes the amplitude of the D-double-prime reflection seems to vary. Sometimes you have the amplitude, if you look at the bottom left figure, the amplitude, the PDP goes, not the amplitude, the polarity, PDP goes down and up, and PCP also goes down and up. So you have the same polarity of these two waves. And that would indicate for the PDP a velocity increase. But if you look at the figure above it, if you look at PDP, it's an up-down swing, whereas PCP is a down-upswing, and P is also a down-upswing. So it's the opposite polarity, so that would indicate a velocity decrease across the double prime. Interestingly, the S wave doesn't seem to show that. This is, or seems to be only for P waves. And the question is, why would this be? It's very likely not a thermal cause, so maybe a cold slab or so, because then we would expect this for both waves to be exactly the same. That leads me to possible causes of the D-double prime region. So we have a layer, a D-double prime reflector, possibly a second reflector, we have topography. And before 2004, there were a number of ideas what it could be. It could be the top of a slab that we're seeing. It could be a chemical boundary layer, a thermochemical boundary layer, or it could be some sort of a hybrid model and so on. But then in 2004, post-perovskite was actually discovered in experiments and also predicted theoretically. And post-perovskite is the high-pressure form of bridgemanite, and the transformation from bridgemanite to post-perovskite will happen somewhere around 300 kilometers above the Comanche boundary, which of course was really nice and good news. People have looked at this a little bit further, and these reflectors, post-perovskite phase transition can actually explain both the reflectors, the top reflector with the strong topography and also a bottom reflector, because if the core is fairly hot, we enter the post-perovskite stability field and exit it again, generating two discontinuities that we might see seismically. So at least in cold and normal regions, we should see this reflector, and we should also see possibly a second reflector. We can also explain these polarity observations of P and S waves, because the post-perovskite has a very strong reduction in bulk modulus, and therefore has a small reduction in P wave velocity, whereas the S wave velocity is increasing, shown there by the two red circles. So post-perovskite can actually explain quite a lot of our observations, but as Jeannot just said, or seismologists like difficult things, so there's still many unanswered and open questions, and I'm only going to talk about a few here. So we find the D-double prime reflector in many regions, and usually around 300 kilometers above the Comanche boundary, but with strong topography. But we also find it in these low velocity regions that we usually interpret as hotter than average mantle. But if you look at the hot mantle geotherm there, and also the seismic profile on the right, there shouldn't be a reflector, but we still see a reflector. So maybe post-perovskite is not the correct explanation, or maybe we just have to mix it with more iron and more aluminium, then we will get a reflector again, but it has other shortcomings. So maybe we should think about that. The other thing is we do detect strong topography, but then if we use rays to travel down and up again, if we have a flat reflector, then usually where we interpret our reflection is clear. But if we have a topography, then our reflection will not be where we think it is, right? Because the path may be different. This will also have some problems for the amplitudes, because basically topography will either or decrease amplitudes due to focusing and defocusing effects. The other thing is that the velocity contrast and the polarities, they're really strongly variable, even in one region. We have in one region also evidence for, or we find events there where there's no evidence for PDP waves or SDS waves, while right next to it, there is evidence for it. So we can make up all kinds of difficult models to explain this. And on top of that, there's directional dependence of both the polarity and also the amplitude of our seismic waves. So the question is post-perovskite really the best explanation? And so we have done one little study recently by one of my PhD students, Vanessa Hima. She put a layer of scatterers into the D-double prime region. And she didn't make it a layer of scatterers, but she actually had like a transition from highly scattering at the core mantle boundary to about 700 to 1,000 kilometers above the core mantle boundary. And so she tried lots of different tapers, she tried different models, And what you can see on the right side over there is that at the top we have an observation of what we would call a PDP wave, and the synthetics at the bottom. This is due to a scattering region with a very long taper, so there is no sudden onset of scattering, which could be the cause, of course. But you can see there is information, there is a wave that we could call PDP wave, right? And we even see variations of polarities and amplitudes in the synthetics. So maybe there are different explanations still. But then, of course, what is the scattering? So, what can we do to verify the double prime structures and our interpretation? And one of the things that I think is really important for all seismologists is to start multi-phase approaches, using different ways that sample the same structure with different azimuths, different directions, different angles of incidence, and so on. And as an example here on the left, I showed a study that my student Angelo Visconti has done, where he used reflections and splitting at the same time, and I'll show a bit more in that on the next slide. But what I think this will help us if we use multi-phase and multi-technique approaches is we might find out how unique are our interpretations, and that's why I put the elephant up there with the blind man and the elephant, because possibly if you only look at one phase with one method, you might only see one part of the elephant, and then you might interpret this as one thing. But if someone else uses a different wave, but on the same place, he or she might see something different, he might interpret this differently. So I think using different methods and waves at the same time will help to see how unique our interpretations really are, and how our choice of method will actually affect our interpretation. And how do other structures affect our measurements? I think that's also a really important point that we have to keep in mind. Okay, going back to the multi-phase approach. So Angelo Visconti has used reflections of P waves and S waves at the D double prime layer, and he also looked at splitting of SCS waves in the D double prime layer. And the idea was that we use anisotropy, or we try to constrain anisotropy in D double prime. One of the possible positive things of using this multi-phase approach is that we can use one azimuth only and try to constrain the anisotropy instead of using lots of different directions, which is really difficult to find. What we do need is knowledge of deformation for different minerals, and what I showed here on the right side is lots of different cases where Angelo has calculated the P-wave reflection coefficient, the S-wave reflection coefficient, and the SCS splitting. And you can see that in the first case we have, for example, no phase transition, so we have bridgemanite from isotropic to anisotropic bridgemanite. And then you can see in the figure with the blue and white, from the inside to the outside is the epicentral distance, and from the top in the azimuthal range is the direction from the deformation. And you can see that for each of those cases, the P-wave reflection, S-wave reflection, and the splitting are different, except for the splitting in the second and third row, because it's the same slip system, so they have to be the same. But using then the data to try and constrain, or to try and explain the data with any of these models, you can actually find out which of the models really is appropriate for a certain region that you look at. And so Angelo has done that, and he has done that for the Atlantic, outside and inside this red area, which is related to the large low velocity anomaly. And you can find that on the outside there is a phase transition from bridgemanite to post-perovskite, and inside this low velocity anomaly there seems to be bridgemanite. And as we tried to publish this, the second paper or another paper, an earlier paper came out that found exactly the same interpretation that we have here. So because we're here 40 years at Geoscope, I thought, okay, what can actually Geoscope do to help us? And if you look at our map up there, it's very sparse. So there's not that many points that we can sample unless we use things like Geoscope stations, and not receiver arrays, but source arrays. So we have lots of different earthquakes recorded at one station, and then we start using source arrays. It actually, we have tried that, and that's the master's thesis of Björn Hein, who is now in Oslo and is now a postdoc already in geodynamics, right? And he looked at all the different Geoscope stations that you see here on the right side, and he did source stacks. What was difficult is to do normal Vespergrams, so just looking at the angle of incidence, but we actually had to go to 3D array techniques. And he looked at all these data, and we found indeed some evidence for a D-double prime reflector in some of those, and my figure apparently has moved a little bit, so it should be on the lines. So we found evidence where the Y's are, and we have something where we're not quite sure where the question mark R's are. So really, Geoscope will help and does help, because it will fill some gaps that we currently can't fill with a normal data or our receiver arrays. So in summary, we have the low-most mantle that is very heterogeneous, structures on a large number of scale lengths length scales are found. On average, the D-double prime reflector is at 300 kilometers above the chromatic boundary, but we do find strong topography. We have variable velocity contrasts and directional dependence of properties, and also a second reflector. So it's all not quite easy. At the moment, the Bridgmanite to post-perovskite phase transition seems to be a good explanation, but there may be different explanations that are better. And I think that we need to verify interpretations and also the structures that we see through multi-phase and multi-approach studies. And also using source arrays, for example, Geoscope. Thank you.
Thank you, Tina. Are there any questions for Tina?
At some point you said that you may not find the wave reflected at the post-perovskite because in hot region. And what about how is it well constrained that you have a correct temperature that you expect in that?
How well constrained is the temperature in the Earth? Well, not very well, indeed. Yeah, so of course it could be that you still see it if the temperature at the chromatic boundary varies strongly. But I think at the moment they're going towards the, I think, was it 4,000 degrees or so at the chromatic boundary. I think the error is quite large. Still, I think in the hot regions, it seems to be a different cause. Partly also from this study from Angelo, where the reflection polarities and splitting taken together seem to indicate that it's more Bridgmanite than post-perovskite. So maybe we can use the seismology to constrain the temperature in the future.
Thank you. I think we have to move on to the last talk of this session given by Durand Barruol. And he's talking about more regional studies of geoscope data in the Pacific, Indian, and Antarctic experiments. And he's showing examples from mental plumes to environmental stuff.
Hello everyone, so thanks to be here today for this anniversary. So in this short talks, I wanted to make some flashback on the free experiment, one being still online, in which Geoscope station has been provide backbone information to temporary experiment. One in the Southern Pacific, one in the Southwest Indian Ocean, and a presently running experiment in Antarctica. So the first experiment I wanted to speak about was dealing in the origin of the hotspot and of the mantle plume associated that generated the hotspot in the South Pacific in French Polynesia. And in the early 2000 year, we were dealing with the model proposed by Courtillot with the origin of the mantle plumes, either coming directly from the CMB or they derived from a large low velocity structure in the lower mantle and propagating as instability towards the surface, or as just like asthenospheric structures feeding the hotspot at the surface. In order to test and to image the mantle structure and the mantle flow, so we deployed some stations over the different archipelagos in French Polynesia. So this the hotspot track. So there are the Society hotspot, the Austral hotspot, the Marquesas hotspot, and the Pitcairn hotspot here. So lie on the oceanic crust from 30 to about 100 million years old. So it's a quite large variation. And in order to test this and to image the mantle structure, so obviously we use the permanent station, the IRIS station, the CEA station deployed in the archipelagos, and obviously the PPT station, the Geoscope station here. So we also deploy 10 broadband stations in various atolls and islands from French Polynesia, and the example of Marquesas station here being deployed by Eric Debay. And so we also combine the observation with ocean bottom seismometers between the archipelagos. So this part of ocean bottom deployments were performed with Jamstead colleagues, Daisuke Suetsugu, with the first deployment of a station between the different archipelagos in French Polynesia, a second small deployment following in 2004, and then higher resolution deployment just above the Society hotspot in 2009. One of the first results that we obtained was published by Alessia Maggi, who's here. So, so obviously, including the 10 broadband stations in the Southern Pacific, where there was very little stations, strongly improves the resolution, particularly in surface wave tomography. It can be seen in the size of the Voronoi cells that correspond more or less to the resolution in the model. So we retrieve some low velocity associated to the asthenosphere mantle and to the ridge, obviously. And particularly what was interesting in this experiment that she succeeded to enlight some low velocity structure beneath some of the hotspots, quite a superficial anomaly beneath the Marquesas and quite a deeper anomaly down to the transition zone for the Austral and the Society hotspot. She also made some anisotropic inversion in which that was dominated by the motion of the plate. And we investigate at higher resolution, so the anisotropy with SKS splitting. What was interesting at terrestrial and ocean bottom station, and we retrieve this northwest southeast trending anisotropy that suggests a strong link with plate motion in this area. We retrieve this APM related pattern in some places, some scattering of the regions that suggests the presence of 2 layers of anisotropy. One lower layer induced by the anisotropy presently flowing beneath the moving plate, and another layer corresponding to the frozen structure within the lithosphere corresponding to the paleo-spreading direction. Surprisingly, so we did not succeed to find any splitting direction, at the station PPT, despite the 15 years of data that we analyzed at that time. And it was also particularly surprising because we observed some clear signal of anisotropy by using the P-wave polarization deviation that induce some of this sinusoidal deviation pattern typical of upper mantle signature. In order to of upper mantle anisotropy, in order to reconcile with these quite paradoxal measurements, was the idea that the two waves do not sample the upper mantle at the same incidence angle. The SKS wave propagate vertically and perhaps sample the mantle with along an isotropic direction associated to the upwelling of the society of spot, which is very close to the Tahiti Island, and the P wave traveling with at a higher incidence angle, and then sampling less perturbed upper mantle in the lithosphere and the asthenosphere. The Japanese colleagues also used the temporary and permanent station in order to make some imaging of the body wave tomography of the area down to the coronal boundary, and they provide some image with low velocity structures up to 1,000 km depths associated to this well-known large low velocity province, and above this 1,000 km depths, so they evidence some small scale structures in the uppermost part of the upper mantle and in the transition zone, corresponding to likely to small scale instabilities connecting with large scale low velocity structures and the hotspot at the surface. This could be a good example of thermochemical dome and secondary plumes that were proposed 2 decades ago by Anand Davai. We also use the station in Tahiti to record some environmental activity, and particularly here is a correlation of the microseismic noise recorded on land, and this microseismic noise induced by the ocean activity. Here's the primary microseism. This is the little peak between 10 and 20 seconds period, and we can clearly see the good correlation of the amplitude of this microseismic peak with the swell 8. Here is the model, the swell 8 from the Wave Watch 3 model, suggesting that the terrestrial seismic station can be used as a wave gauge on oceanic islands. The second example I want to speak about is taken from the Durand experiment in the southwest Indian Ocean, in which also it was a Réunion spot and upper mantle Réunions interior mantle. It was a project, a French-German project carried also by Karin Sigler, and in which we deployed 58 OBSs around La Réunion Island here and on the southwest and central Indian ridges. And obviously, adding this data, but also some companion experiment brought by the US, the Makumo experiment, and also the Sela-Soma experiment provided by the BFZ colleagues. Of course, it provides a much higher resolution and a much better resolution in imaging the upper and lower mantle. One of the first results was provided by Alessandro Mazzullo in his surface wave tomography of isotropic and anisotropic velocities. To make it short, so we make it very short, so we observe here in Venice Mascarenes Basin a quite thick and fast lithosphere with a north-south trending anisotropy. We also observe a low velocity channel connecting La Réunion hotspot and the central inland wind in this region. And in the asthenosphere, we found what a large low velocity anomaly in the asthenosphere between 100 and 200 km depths that we call the Mascarenes Basin asthenospheric reservoir, and which is also characterized by a northwest southeast trending anisotropy. In cross section, so we clearly see this lithospheric structure above the slow anomaly, the asthenosphere. This slow anomaly spreading clearly beneath the central inland ridge and going also in the upper mantle beneath the Indian plate. When one zoom in this area, so we retrieve the north-south anisotropy within the lithosphere above this anisotropic low velocity structure in the asthenosphere, and so we found also a pattern of spindle-shaped anisotropy within the asthenosphere, suggesting a kind of forced flow in the asthenosphere, and then and therefore a decoupling between the atmospheric flow and the overlying lithosphere that was moving more or less towards the northeast. So for mesochemical imaging, so we observe this large-scale horizontal flow in the atmosphere along the Réunion Central Indian Ridge Channel over more than 1,000 kilometers. And this large low structure beneath the Mascarene Basin associated to large anisotropy, which suggests that hot plume material could be trapped beneath the lithosphere. And we also evidence this strong lithosphere-atmosphere decoupling in this area. Using all the temporary and permanent stations, so Karin Ziegler and her students at that time, so Maria Zekmistenko, used all kind of information to make body wave tomography, and so they inverted more than 2.5 million of information in terms of velocity and structure of this area. And to make it short, so I will. This is a 3D cartoon of the structure, and here is a map of the core mantle boundary. And as we go from the bottom to the surface, here we observe some large low velocity structure beneath just above the CNB, so at the bottom of the lower mantle, which is trending more or less northwest southeast. And as we go upward in the lower mantle, this structure focuses here more or less beneath Mozambique as a chunk here in yellow. And as we go upward in the lower mantle, the structure also still separates in different branches, going southeast toward Kerguelen and northward toward Afar, and also northeast toward La Réunion. So this suggests that this clearly enlightens the fact that there is not a common branch, continuous branches going from the lower mantle to La Réunion, but it's kind of a blobby structures going from the lower mantle to the surface. And also it shows that genetically this different hotspots could have some common origin in the lower mantle. In cross-section, as shown by Stephanie a few minutes ago, we are left with a very complex structure, with a blobby structure connecting the large low-velocity structure beneath South Africa and La Réunion. And in 3 dimensions, this blobby structure is obviously complex and asks a number of questions to geodynamicists. And that's also a reason for which we propose that this blobby structure can be related to the fact that it could be related to instabilities starting from the lowermost mantle and going upward and feeding the different hotspots and detached at different time in space at the lowermost mantle. We also use area station in La Réunion to make some environmental analysis, and here is an example of cyclone climatology from the RER station. So the Southwest Indian Ocean is a quite active area with cyclone, and here is just an example of the season 2018-19 as seen by the station RER with numbers of cyclones crossing in this area. And we can clearly retrieve the signature of this cyclone in the primary and secondary microseismic maps, so I will not detail the story, but we can retrieve long-term climatologic information in this kind of station. From the deployment of large or broadband instrument on the ocean bottom, we also developed some exotic work, particularly the cyclone tracking from ocean bottom. The use of ship noise as recorded by the ocean bottom to relocate and orientate the OBS on the ocean bottom, but also the idea is also to detect and track ships from passively from ocean bottoms, and also to use OBSs even at great depths to detect and track big mammals in the oceans. The last example I wanted to speak about is in Antarctica, the station Durand, which is really the connection between the continent and the ocean in this area, south of Australia, and very close to the Astrolabe Glacier, which is a good place to make some cryoseismic experiments. So 10 years ago, I was involved in the Arlita project, carried by Jérôme Bascou in Saint-Étienne, in which we worked on the boundary of to track and to quantify the boundary of the East Antarctic Craton in the Mercer area. So it's somewhere here. So we deployed a few temporary stations along the coast, particularly to measure the velocity structure between in the crust and also the depth of the mold in the different places, and also some anisotropy measurements at this area. And but now, I'm focusing on the activity of the Astrolabe Glacier, which is very close to the Durand station. The Astrolabe Glacier is flowing from the ice cap toward the ocean, and the idea is to monitor the interaction between this flowing glacier with the ocean, and particularly with the warming ocean, in order to see the effect of the changing climate on the dynamics of the ice in this area. So Durand is particularly well located between the cryosphere, between the water and the continent. And here is an example of the ocean activity recorded at Durand. It's an example of a very strong sea ice breakup that occurred in September 2020 at Durand, and it was in fact induced by here you have one or 2 weeks of record at Durand. This is a spectrogram, and it's and the breakup of the sea ice occurred on the 6th or 7th of September, and it was in fact induced by a very strong storm traveling between Australia and Antarctica that hit the external part of the sea ice and broke the sea ice across its whole broadness, that is to say several hundreds of kilometers up to the continent. And a second effect of the swell was generated by the second peak of the swell that traveled from the west to the east and finished to break the ice close to Widmer-Schnidrig. So deploying station in this area is obviously interesting to characterize and to characterize the processes that occur by crevassing, for the quantifying the subglacial flow, the basal slip, but also to look at what happened in the ice in the ocean offshore, the interaction of the sea ice, the icebergs, and also of the bioacoustics occurring in this area. So we have been deploying a few months ago some semi-permanent station around the glacier here, and a temporary experiment on the grounding line of the glacier. The grounding line being the place where it goes from landed to floating at this area. And we also deployed some OBSs just in front of the terminus of the glacier. So the data are extremely rich, and particularly because we observe here we have an example of 1 hour of record on the grounding line at a different station on the grounding line of the glacier. We record numbers of events induced by crevassing, repetitive events like these little tiny events, probably linked to a stick slip displacement either on the base of the glacier or on the lateral faults, and numbers of tremors that illustrate probably some subglacial hydrology. We also clearly record the tide-induced ice quakes. Here is 1 week of record on the grounding line. So we see this daily modulation of the signal, and particularly the occurrence of these ice quakes every day, likely induced by the tide activity, and also the development of tremors, daily tremors, probably indicating the modulation of water activity beneath the glacier. The tide-induced ice quakes are clearly visible at station DRV. Here we have the occurrence of ice quakes, the number of ice quakes detected at DRV by STA, LTA algorithm. So it's about 100, 150 events per hour in red, and above the tide level in blue. And it's clear that the peak of the ice quake occurred during the descending tide at DRV, showing that there is some kind of brittle activity related to the vertical motion of the ice floating tongue in this area. We also deployed some OBSs close to the tongue of the Astrolabe glacier. It was the first deployment of few instruments during a few weeks, and the redeployment of 2 instruments that are still on Benes, that are still recording for 1 year, and that will be recovered the next January. So now the presence of sea ice allows to make some active seismics just above the OBSs. So some concluding remarks. So thanks to the energy that had been put in the managing this network, so we have a very high quality of data from Geoscope. Obviously, long-time series that provide a primary importance for temporary experiments, and they clearly provide instrumental backbones in the scientific exploration of the data. And if Geoscope were initially dedicated for deep Earth studies, now they are clearly much broader applications. And one of the messages is the environmental applications really need some perhaps either some dedicated sensor or at least some higher sampling rate at some station. Thank you very much.
Are there any questions? Questions? We go on.
Hi, thank you for this very broad talk, many insights. It's a rather specialized question, but on your picture for PPT and your correlation between the ocean swells and the seismic noise, there seemed to be like extremely good correlation kind of in the big picture, but if you look, there seems to be either a phase shift or at least the symmetry of the sort of increase and decrease seem to be there, so like lack of correlation in the detail. Can you comment on that at all?
Hard to say so, because in this situation, so there was no wave gauge in Tahiti, so we compared our seismic measurement with the model of waves, the wave watch-free model, so we can have some time shift in the arrival of the waves, so that can be a possibility. Otherwise.
Okay, I think it's time for refreshment. I suggest that we thank the speakers, but also the organizers, for organizing this wonderful workshop, which, at least for me, takes us down memory lane so nicely.